Hey everyone, and welcome! Today, we're going to dive into one of the absolute biggest challenges in tech right now. How do you actually build a quantum computer that's powerful enough to, change the world? We know that a single quantum chip can only get you so far. The real puzzle is figuring out how to scale up.
Just think about it for a second. For the classical computer you're watching this on right now, the answer is, well, it's a solved problem. When one processor just isn't enough, we know exactly what to do.
You just link up thousands, even millions of processors together with a super high-speed network, and boom, you've built a data center. It's the engine behind our entire modern world, from the internet to cloud computing. Simple enough, right?
Well, here's the thing. The moment you step into the quantum realm, that entire playbook gets tossed right out the window. The physics of linking quantum processors together is just fundamentally different. It's an absolutely incredible engineering challenge. So let's get into why that is and what engineers are doing to write a whole new playbook for the quantum age.
Okay, so this gets us to the heart of the quantum scaling problem. A single quantum processing unit, a QPU, can only pack in so many qubits before it just gets way too unstable and noisy. But to solve the really big, world-changing problems, we need a lot more. The idea that's getting everyone excited is something called distributed quantum computing.
And the core idea of DQC is just brilliant in its simplicity. It's like if you can't build one single massive perfect quantum processor, well, why not just link up a whole bunch of smaller, more manageable ones? You can take a big quantum algorithm and split it across all these different QPUs, creating this one giant, powerful metacomputer. But to pull that off, you need a network. And not just any network, you need a quantum network. This incredibly specialized fabric that can physically connect these QPUs. This quantum data center requires some really unique, really cool pieces of hardware.
So first up, you've got the QPU itself. The QPU isn't just doing the thinking. Yeah, it has its data qubits that are running the calculations, but, and this is crucial, it also has special communication qubits. Think of these as the on-ramps to the network, letting it talk to all the other QPUs using light.
Next, we have the optical switch. Okay, so you can pretty much think of these as the traffic controllers for this quantum internet. Their job is to constantly reconfigure the pathways for photons, directing the flow of quantum information so that the right QPUs can talk to each other at exactly the right time.
And then there's this thing, the Bell State Measurement Module, or BSM. Now this is a purely quantum piece of kit. Its whole job is to act as a referee. When photons from two separate QPUs meet up and interfere in just the right way, the BSM shouts out, "Success! You are now entangled." That means the fates of those two qubits are now linked no matter how far apart they are. Pretty wild.
So, you've got your QPUs, your switches, and your BSMs. These are basically the Lego bricks you need to build a quantum data center. But, as any engineer knows, the blueprint, the actual architecture you use to connect all these pieces, well, that changes everything. And it turns out there are two totally different schools of thought on how to do it.
And this brings us right to the central conflict, the big debate that's explored in the research we're looking at. It's a clash between two fundamentally different philosophies for how you should design a quantum data center from the ground up.
On one side, you've got the switch-centric approach. In this world, the QPUs are basically just endpoints. All the heavy lifting, all the smarts for routing quantum information happens in this complex web of optical switches. But on the other side, there's the server-centric philosophy. Here, the QPUs themselves are active players in the network. They act like little quantum repeaters, helping to pass entanglement along the chain.
And this image, wow, it just lays out the difference perfectly. Look at the top, the server-centric model. To get a connection from QPU1 all the way over to QPU7, the path literally goes through other QPUs, like Q4 and Q5. They're part of the chain. Now look at the bottom, the switch-centric model. The QPUs are only at the very beginning and the very end. The entire path is carved out by that web of black icons, the optical switches themselves.
So these two philosophies aren't just abstract ideas, right? They lead to very real concrete blueprints for how you'd build one of these things, and each one has its own set of pros and cons. So let's meet the specific contenders that were put to the test in this research.
The paper digs into four main architectures. Three of them, Fat Tree, Close, and Q-Fly, are all from that switch-centric school of thought. They're actually borrowed from the world of classical supercomputers. And the fourth, B-Cube, is the lone server-centric contender, representing a totally different way of thinking.
So those switch-centric designs, the ones inspired by classical data centers, they're all about things like creating lots of different possible paths, or making sure the paths are as short as possible.
Their success is deeply, deeply tied to the quality and the sheer number of those optical switches.
B-cube, on the other hand, takes a completely different path. It makes a trade. It says, okay, we'll rely less on all that complicated optical switch hardware, but in return, we're going to rely more on the QPUs themselves. The QPUs have to be good enough to act as these little quantum repeaters, holding onto those super delicate entangled states.
So here it is, the million-dollar question. Which one actually works better? When you simulate these designs under realistic conditions, with all the messiness and noise and loss you get in real quantum systems, who actually comes out on top?
Well, the results show it's all a game of trade-offs. The designs with tons of switches, like Fat Tree and Claws, they give you lots of different paths to try, but man, they are super sensitive if those switches lose photons. Qfly gives you shorter paths, but it needs more powerful, more expensive switches. And B-Cube, our server-centric model, it doesn't care as much about switch loss, but its performance is completely dependent on how long its QPUs can stay coherent. Basically, how long they can hold their quantumness before it all just falls apart.
And check this out. Here's a really fascinating, kind of counterintuitive result from the study. You'd think fewer switches is always better, right? Less hardware, less loss. But they found that if you have plenty of those BSM modules, the entanglement heralds, the architectures with more switches, like Fat Tree and Close, actually perform better. And why? Because in those designs, every switch has its own set of BSMs. So more switches means you have this huge distributed pool of BSMs, and the system can try to create many entanglement links all at once, all across the network, which just dramatically boosts the odds of success.
So where does all of this leave us? Well, it leads us to something we can call the quantum architect's dilemma. The data is pretty clear that there is no simple, one-size-fits-all answer here. And this quote from the paper's abstract, man, it just sums it up perfectly. It says that performance isn't just about the network layout. It's this really complex dance between the architecture, the software that's scheduling everything, and the actual physical quality of the hardware itself. And the key part is all of these things interact in really complicated, non-obvious ways.
So the bottom line is this. There is no magic bullet. There's no single best architecture. The right blueprint for a quantum data center depends entirely on the technology you actually have to work with. If your optical switches are really lossy, a server-centric approach like B-Cube might be the winner. But if your qubits can't hold their state for very long, a switch-centric model is probably your best bet. It's an incredibly delicate balancing act. And that leaves us with the ultimate question, doesn't it? As engineers keep getting better and better at building the individual components, this research gives us the framework for figuring out how to put them all together. The final blueprint for the first machine that truly unlocks the power of quantum computing? Well, it's still being written, and it is going to be an absolutely fascinating story to watch unfold.